In this video, I want to look at what I think is one of the most interesting integrals in all of calculus. So let me begin this by posing the question: if I have the integral of u, where u is some function of x, raised to the negative first power, what is its antiderivative? Well, you may think, oh, well, we can just use our power rule. And our power rule says that the integral of u to the n power will be u to the n plus 1 over n plus 1, just raising the power 1, dividing by the new power, and obviously plus c since it's an indefinite integral. But that doesn't work here, because if we tried to do that, that would become u to the negative 1 plus 1 over negative 1 plus 1, which is u to the 0 over 0. And we can't have that. The power rule doesn't work there. So our rule doesn't apply if u is negative 1. So what can we do to integrate that? Well, this is where I think it gets really fascinating. If we think about our derivative for the natural log, we know that the derivative with respect to x of the natural log of u is equal to, and u being a function of x in this case, the derivative of u over u. Well, if we just integrate both sides of this equation, what will happen, the integral and derivatives cancel one another. We get the natural log of u is equal to the integral of du over u. And du over u, well, that's the same thing as u to the negative first du. So we find that in this one instance, when our power rule doesn't work, we can use natural logs. But one thing I must say before we continue on with this rule is when we're taking the derivative, it's pretty straightforward. Remember, when you're integrating this, one, you'll need your plus c there. Secondly, you actually need absolute values around your u. And that is because in the case of the derivative, you don't really have to worry that much because you're getting an algebraic function back. When you're integrating an algebraic function and you're getting a natural log, the natural log can't be evaluated when the argument's negative. So if u is some negative value, you can't evaluate that. So if we want to find area under a curve or use it for other applications, we need to take the absolute value of u to ensure that we're able to evaluate it and it's not undefined. So I'll write out our basic rule nice and clean, that the integral of du over u, which is the same as u to the negative first du, well, that integral is the natural log of the absolute value of u plus c. So what does that look like in a real example? Well, say I give you the integral of x plus 2 over x squared plus 4x minus 3 dx. So what can we do with that? At first you may think, oh, well, that looks a little bit complicated. I don't really know what to do with that. But let's make a simple substitution. If u is equal to our denominator, x squared plus 4x minus 3. What is du? Well, it'll be the derivative. We'll just use our power rule, sum and difference rules here. That's 2x plus 4 dx. Well, if you notice, our du is just off of the numerator by a constant multiple. We can say du is equal to 2 times x plus 2 dx. So we can rewrite this integral as the integral of 1/2 du over u. And we know from our previous example, or what I've shown with our rule, that that integral is just going to be the natural log of u. So we'll get 1/2 times the natural log of the absolute value of u plus c. And then just substitute back. It's 1/2 times the natural log of the absolute value of x squared plus 4x minus 3, our u value, plus c. And that's the antiderivative. And we can use this rule in a lot of different ways as we go through calculus. There are many instances where we'll find a situation with a function in the denominator and its derivative in the numerator, or a slight alter, something slightly different. We may have it off by a constant multiple as we saw here, and we may be able to do a little slight manipulation to get it into that form. So these integrals resulting in natural logs can be really useful for us to integrate a lot of functions that we previously couldn't.